In the second part, we will talk about unsupervised localization and classification. Okay. Now, we'll talk about something called class activation maps. Now, what we've seen previously is that classification is equal to predicting class assignments for a given image. And we have also seen that localization means determining the location of an object. Now, it looks like unrelated to these, but in the last hour, we also studied the visualization of the extracted features for interpretation. Another question that we can ask in terms of interpretation is, where does a network look at in an image? Specifically, if I want to, for example, classify an object, right, I have to look at somewhere in the image. A natural question to ask for a neural network to understand how it's working, to interpret its mechanisms, is to ask, where does a network look in an image? And we will specifically look at it for the classification task, partly because it's easier, and partly because extension to other tasks are a little bit more harder. So we will only look at the classification tasks. And we will specifically study the article from Zhu et al., Learning Deep Features for Discriminative Localization. The idea is something very simple. It will be based on global average pooling. And you can follow the discussion from this 2016 paper. But what we want to get at is, if I want to classify an image in terms of the action that's actually going on in the image, I want to be able to create maps such as these ones, where we see that in order to classify the image into the category of cleaning the floor, the network looks at these areas or highly weights these areas in the image to determine what's happening. And for a given image, if the image changes, obviously where the network looks in the image changes as well. This happens for all classes: cleaning the floor, the cooking. As you can see, the network starts looking at the food on the table, as well as changing tires, for example, fixing a car. Okay, so these are the type of maps we want to look at. For example, when I look at the fix at the car, we see that the network identifies the wheels, looks at those regions, looks at the car, and decides that, well, I think there is something like someone is fixing a car. And here, the image changes. Network now look at inside the car structures to classify that, okay, someone is fixing a car. So how does this work? We will see how these maps are created for a classification network. And this strategy can be applied for any network, actually. And we can start from the generic network that we created in the previous lectures. Here we take an image, we feed it into convolutional connections into different layers. These are convolutions followed by rectified linear units followed by max pooling. And at the very end, I basically convert this tensor, vectorize it, and apply fully connected layers to end up with class assignments. Now, the last part here is simple. I do a linear classification. The information in this layer is actually quite complicated. Here, each of these neurons have very large receptive fields, and they extract quite complicated features that we've seen in the last hour as well. Now, the class activation maps takes a very different approach to identify the regions in the image the network is looking at. So, instead of actually going from the image directly to this vectorized form and then doing a linear classification, it does something else. It actually replaces these maps with a map that's of same size as the image. So it actually takes this tensor and it upsamples it using transpose convolutions like we've seen before in the last hour, or using bilinear upsampling followed by convolutions. So instead of converting this into a single vector by vectorizing it, I now convert this into a huge layer that has channel size equal to the size of the image. Then I apply something called global average pooling. It's a fancy name for something very simple. Now, this layer is formed of multiple channels. Each, again, has a channel size that's the same as the image size. I simply average this tensor across the channel direction. So I basically, if I have, let's say, 10 different channels in this layer, I simply convert it into 10 numbers. Mathematically, what it looks like is it acts like a normal pooling operation, but it applies to each channel differently. So I really take the channel and average across the XY direction, across the channel size, to convert this guy into a single number. And it might sound extremely cruel because I average all the information to a single number, but it actually works quite well. Then I continue as usual. I simply, if I have 10 channels here, I convert into 10 numbers. Now I have a hidden layer of size 10. So I can do linear classification, just like I did in the past. Now, what does this look like? How do I actually get the activation maps from this? Now this is another version of it. So I took this layer and I upsampled it to a huge layer that has the channel size equals to the image size. Then I do the global average pooling, so converted each of these channels into a single number. Then I applied linear classification with a logistic regression, as we did before. So in order to get the maps, what I do here is I take the class here. For example, this image has an Australian Terrier. And I simply compute the probability here, okay? And now I want to create a map that activates this class output. So I take this class, I compute or determine the weights that actually connects this output to each of these inputs. And remember that each of these inputs here are denoted as neuron, a single number, but they are the average of this entire image. So you can imagine that actually this weight not only multiplies this neuron, but multiplies every pixel in this blue channel. So I can simply say, okay, so let me get this channel and multiply it with the weight here, W1. Let me get the other channel and multiply with W2 and so on. And instead of averaging these channels, let me actually keep them in the channel size and simply find the sum. And this sum kind of gives me the activation necessary to activate this Australian Terrier output. In this specific example, I see that actually the network, the high weight areas correspond to the dog itself. So in order to really get a positive response here, remember, this is logistic regression in the end at this layer. So a positive response means that everything, the values here should be very high. I need positive contributions from all of those. So I can simply look at the positive areas that are coming from each of these channels after multiplication with the weights. So per class weighted sum of all the channels before the global average pooling yields me the class-specific activation map. I can do it with multiple examples. These are the ones that I've shown you from the Stanford Action 40 data set, basically identifying the action that's happening in the image. But you can imagine that you can apply the same technique for any type of classification problem, and that's what they did in the paper. Now, the network that actually comes before the global average pooling can change, can be anything. For example, we've seen the residual network, the ResNet before, and ResNet, for example, at the end uses a global average pooling there. But you can put anything there, you can create your own network. The only important thing is there's a global average pooling. So first, you take the final penultimate tensor in the convolutional layers, convert it into a very large layer that has multiple channels, and each channel has the size of an image, and then you can do global average pooling. And this is kind of also acts like a form of weak supervision for localization. Because notice that actually, if I want to locate horses in these images, these class activation maps gives me quite a good idea where the horses are, and so on. And this has multiple applications, especially in the medical imaging where interpretation is important. You really want to understand where the network is looking at to decide on the class. For example, in this work from a friend of mine, Nicolas Toussaint, what they did was they basically tried to create a network that understands the image, an ultrasound image taken prenatal. So the network decides what they see in the image, and they use class activation maps. And when they look at the proposed class activation maps and put them back on the image as an overlay, they were able to really identify the structures the network looking at, and it actually served as, for example, here in this case, we're looking at the limbs, and this really highlights the limbs of the baby here. And this has an additional use. So first of all, it identifies where the network is looking at, so that's actually great for interpretation. Second, labels are quite expensive to get. So if I want to create a neural network or a machine learning algorithm that locates different structures in the images, I can either take all these images and have an expert sit and identify all these areas, or I can use such an approach that already identifies the locations, maybe not perfectly, but in an okay way, and use these kind of semi-wrong, not completely right labels for the localization to train another neural network to do the localization itself. And that's what's called the weak supervision to train a strong localization algorithm. And in the paper here, they show that this is possible using class activation maps. Again, before going into the next topic, I'll stop here and upload the video.